That's the bad.
Zero English. And then look at things.
That's wrong.
Yeah, I'd be trying to go out. Yeah, I was like, you could not do that. My friend was like, I told you like it. I'm like, what did we have?
Okay. How's it going? Okay, I asked somebody to remind me of something. Tina? Oh, okay. So all of you received potentially an email from Brittany about the highlights, and they were formatted in a question format. And it seems like it confused some of you or most of you, thinking that you have to answer questions. But these were like prompts of what would you put in under your results section as highlights. So do not think that these are questions for you to answer. These are just prompts for potential highlights, 3 to 5 highlights. Okay. Any clarification on that? Can you you guys let Brittany know that we had this discussion? She might see that some people answered questions that was due to a confusion. It was not meant as questions, prompts. Okay. All right, anything else related to lab report that you want to ask? Okay. All right. Let's do some recap questions. How does temperature impact resolution? Go ahead, Owen. Yes. So higher temperature usually enhances the movement, make you well, not you, the solutes move quicker between the stationary phase and the mobile phase, and it helps reach equilibrium faster. So, thermodynamics in place, and also reduces the viscosity of the metal. So that if you have two peaks that kind of are shouldering each other with a little bit higher temperature, they might become sharper. And if they're sharper, smaller width, you get better separation. But of course, usually when we select a temperature, we make sure it's within the column specification. You don't want to degrade the column. Also, you don't want the movements to be too fast either, because then they won't have enough time to interact with the column and separate. So you have to find your sweet spot in terms of what temperature to use. What about flow rate? Go ahead.
A faster flow rate will increase resolution.
2. So the same thing with faster flow rate, you have better movements. So bringing down the solutes, reaching equilibrium faster. But if you remember the height equivalent of theoretical plane, you need also to reach optimum flow rate. You don't want it to be too slow. That will cause longitudinal diffusion and the peak broadens. You don't want it too fast, then you don't reach equilibrium properly, and then you don't leave the column faster than they should, and you lose separation. So again, finding that sweet spot for flow rate as well. What about packing and thickness of the stationary phase? How does the thickness impact the resolution? Tyler?
The narrower the column, the higher resolution.
Yeah, that's you're answering the one under, which is true. Narrower, longer, you have less material, faster movement, better separation, but the thickness also. Sometimes we have hollow columns with like capillary columns. You have a really thin layer of stationary phase on the inside. So you have less material for the solute to interact with. So you reach equilibrium faster. And then you don't have a lot of diffusion happening within the stationary phase. So that gives you sharper peak. And a lot of the high performance liquid chromatography, not high, ultra high performance liquid chromatography or UPLC utilizes these kind of columns that have kind of a capillary column and very small amount of injection volume because you have very low capacity, but you have very good resolution and fast analysis time, around 10 minutes rather than 60 minutes. And then we answered the narrow question.
Go ahead.
When talking about the thickness, are we, when on silica, are we talking about the thickness of the functional layer on the outside of the silica?
So there are two types of silica. So silica where it is really non-porous and it doesn't have any interaction effect with the compound, and then you have a thin layer of functional groups.
And so that would be the thickness in this question.
Yes, that is one of them because you have that. Okay, let me go back. Why is it not responding? Yeah, so that bonded phase with the inner core. So that would be a thin layer around an inner core, but also I was talking about a capillary column.
Yeah. That again, I was
Yeah.
wondering about what.
Yeah, yeah. And gray.
For the silica and for the core, they're all like spherical, right? Or is it
The
like one-
particle?
Yeah, it's spherical.
Usually your particles are spherical particles with pores within each particle.
So then you have like void space.
The void space is between the particles. So if you have, okay, so your void space is really when you have your so there here in the middle, that's a void space. So your stationary phase is packed, right? But there is void that goes.
So then how do they like make, do they have ones where like the diameter, they have like varying diameters
yeah.
of the sphere?
So basically, the smaller, the less void, the less potential for your solutes to go in and get lost and delayed and diffuse and broadening the peak. So for high performance and ultra high performance, you want very, very small uniform particles to avoid the empty space.
So we'll never put the small with the big one.
No, you usually don't do that. Well, no, usually you don't want to do that. If that happens, of course, you can potentially control the same particle size for everything, but you try, it has to be uniform. It's not uniform, you don't have good decisions. I'm not saying it doesn't exist, but I'm saying you don't want. Yeah, but good, but to, and if we're looking at size exclusion, so you would also pack with very, very uniform, as small as you can get. But with size exclusion, you have those specified pore sizes within the particle that allows you to separate molecules of different molecular weight. And those pores, you would order your stationary phase based on what the molecular range that you're trying to separate. You get pore sizes. Okay, well, thank you for the questions. Okay. Looks like grapes. All right. So what are some advantages of high performance versus low pressure? Like with chromatography, go ahead, Graham. It's faster. Very good, Tina. What's that? Yeah, we can reuse the column many times more than the low pressure, because low pressure we pack. Sometimes we have to wash, repack. Yes, Sophie. Sharper peaks, of course. With low pressure, it's mostly overtones, large white peaks. And we use the low pressure mostly for fractionation and collection of material or fraction at the amount that we can work with for other analyses. And sometimes we use it when we can get enough separation for the compounds we want. Okay. Let's remember gradient illusion. What is gradient illusion in HPLC? You all did the HPLC lab. Was it a gradient illusion for the caffeine? Yes. What did you do? Do you remember what was the gradient? No, we kept the temperature constant. Yes. So we adjusted the ratio of organic solvent to water over time. So because it was reverse phase in that example, we started with 99% water and 1% acetonitrile. Over time, we kept increasing the acetonitrile, I think up to 30%, was it? And then we let it sit at 30% and brought it back to the original percentage so that you can inject a new sample. So gradient illusion is mostly changing the concentration of your mobile phase, or the composition, I would say, of your mobile phase. Composition is more correct than concentration of the mobile phase over time, because it's not always in one direction. It's not always you increase the organic salt. It's not always you increase water. It's not always you increase salt. Sometimes you increase salt. Sometimes you increase the pH. Sometimes you increase water. So it depends on your mode of separation. So it's a better term, remember, to say change the composition of the mobile phase over time. Okay. What is a guard column and what does it do? Go ahead, Kendall. At the end or at the beginning? Yeah.
And then it's basically things that
Absolutely. And these molecules usually refer to them as impurities. So any impurities that will bind very, very strongly to your column and block functional groups, you don't want them to get to your column. So we put this free column or guard column to guard the column from impurities. And we do change it or clean it as often as we can so that the column is protected for the longest time possible. How many solvents and pumps can one use in HPLC? Yes, Gray. 2 pumps? Yes. So, yes, absolutely. The minimum obviously is 1 pump. Often there's 2 pumps. The most common that you see, 2 pumps, 2 solvents. That's most common. But a lot of time you have 1 pump. You can put 4 different solvents that you mix up the composition throughout the run, and you have a 3-pump mixing, low pressure mixing. So you determine the ratio and you have this low pressure mixing, and they all go into the pump and they get pumped into the system at a particular programmed composition. So up to 4, 1 to 2 pumps and up to 4 different mobile phases or solvents for the mobile phase. Yes.
Probably they put with gas in the mobile phase.
Yes. So some systems have a degasser before going into the pump, and before going into the pump. So did you talk about why do we degas? And what happened if you have air bubbles in the system? Okay, so what do you remember, Kristen? Do you remember why?
Because it would explode.
Explode?
They had like gas.
Well,
What was our air bubble?
no, it won't. Wouldn't that been really interesting if this would happen? It will like mess up the movement of the hematocrit. Yes, so it would mess up the retention time. So basically, when you have an air bubble, that's like vacuum, it's a void. So your compound is going through and separating between the mobile phase and the stationary phase. All of a sudden, there's no mobile phase, there's air. So there's nothing to go out to. So it diffuses and waits until there's a mobile phase to go. Then this gives you a delay in the retention. Sometimes the air bubbles also, there are a lot of them that cause continuous spiking of the mobile phase, like the baseline of the chromatogram, because your detector is detecting a baseline, a mobile phase, and suddenly there's nothing that goes through the detector because you have an air bubble. And then the mobile phase comes in, and then it gives you a peak, detecting the mobile phase again. So you get phantom peaks, which messes up your area. Sometimes the phantom peak might come while something is eluting. So you will have really very not, when you see a baseline like that, you know that you have air bubbles in the system. Okay. All right, we good to move on? All right. So the detectors. We're going to talk about absorption, UV, and fluorescence, and all of that. But I want to introduce the detectors that are commonly used with HPLC. The most common detectors are UV vis detectors, UV for ultraviolet and visible light. And here it detects a chromophore containing compounds. So chromophore containing meaning a functional group that absorbs light. They like phenolic compound, they absorb light. And then measure the absorption of that light. So the most common detector is a variable wavelength detector. It's cheaper than other detectors, commonly available. And in this variable wavelength detector, meaning you set the detection at a particular wavelength. Sometimes you can set to read absorption at 2 wavelengths. That would be really nice. And sometimes you set to change the wavelength between 1 minute to 10 minutes, and then between 10 minutes, 20 minutes, you can change that set wavelength. So the wavelength is lambda. What was the lambda for caffeine? Do you remember? 272. Why did you remember why we chose 272 for caffeine? What did Nigel tell you? I'm gonna tell Nigel. Nobody remembered what Nigel told them. Or didn't tell them. Probably didn't tell you.
I think he said you know it because you browned caffeine before.
Sure, but why 272, not 254, for example?
And it's like a fingerprint. Okay.
Sure, tell me more about that fingerprint.
Yeah, so it's particularly strong, like other things we're looking at.
So you talked about something called lambda max. Do you remember this term? I'm gonna hold you accountable for this term. Lambda max, the wavelength at which you have maximum absorption. Because that's where you have the highest sensitivity when you're trying to quantitate. So you want to select quantification or identification at a wavelength where you get maximum absorption. So in the variable wavelength detector from previous studies and experimentation, you would know what's the maximum or the lambda max of the compounds you're measuring. This was for caffeine. But it's different for isoflavone. Some of you did mass spec already. It's 254, for example, is the wavelength for that. So every compound has a particular wavelength where it's determined to be lambda max. So with variable wavelength detector, we can select that if we know it and measure absorption. Now, do you remember what you used for caffeine detection? Was it deuterium or tungsten lamp? Do you remember? Right, but every detector has a lamp. Because even the photodiode array detector, you're measuring absorption of light, but you're measuring absorption of light using three-dimensional data, time, wavelength, and absorption. Huh? Tungsten. Tungsten? No, it's deuterium. Tungsten is for visible light, deuterium is for UV.
Photodiode was on the auto sampler, the UV was, or the deuterium was on the manuals.
Yeah, so usually for PDA, we only turn on deuterium if the range that we're looking for is in the UV range. We don't normally turn on both lamps because we kill the life of the lamp. If we don't need it, we don't turn it on. The visible lamp is tungsten, and if we're not looking at anything between 400 to 800 nanometer, we don't turn it on. It's just to save the life of the battery, of the lamp. Okay. So best sensitivity when we select the lambda mass. And what else did I say here? Okay. Now, the photodiode array detector is what you use in the lab. And I'll tell you the difference. And when we cover spectroscopy, I'll talk about that more in detail. But in UV vis variable versus PDA, so you have the flow cell. This is the flow cell in the detector. So I don't know if Nigel pointed out to you in the system, but you have a flow cell. So your mobile phase goes through the flow cell, carrying your compounds of interest. So when they get to the flow cell at a particular time point, so you have your lamp. In photodiode array detector, all of the light goes to the sample. Whereas in the variable UV detector, there is something called monochromator. We are going to talk about it. Monochromator. So it takes the light, diffracts it into multiple wavelengths, and only one wavelength is selected to pass through the sample, and the sample absorbs at that particular wavelength. In photodiode array detector, we do not have that. So all of the light goes onto your sample, and then the sample absorbs light, and part of this light that was not absorbed reaches the detector, and you get a readout. So that readout is three-dimensional. Here you have the lambda, the wavelength, nanometer, which you already saw in the lab. And here you have your absorption. And this is at time X. You have a readout usually every 0.1 second, kind of, you get a readout. At a particular time, you're going to see a fingerprint of absorption with a lambda max at a particular wavelength. Let's say this is your 272 nanometer for caffeine. So this fingerprint is very specific to caffeine. At different wavelengths, the molecule absorbs differently. And we'll talk about absorption in next when we start talking about spectroscopy. But what I want you to know is really in PDA, photodiode array detector. Photodiode array detector, you are sending all of the light to the sample, and the sample is absorbing at multiple wavelengths. Sometimes you don't get an absorption of, so let's say this is 0. Sometimes you don't get an absorption. At a particular wavelength. Sometimes you get an absorption, but it's not ideal. So you don't want to select this lambda to get absorption because it's not the maximum sensitivity. So you get the one where you have the highest absorption. So PDA not only allows you to quantitate at a particular wavelength, but it shows you at the fingerprint of that molecule. And how is that beneficial? Look at this example. So if you have a regular a variable wavelength detector, and you select a one wavelength, let's say this is what do you read? 250? What is that nanometer? 254? I can't read.
We can't read it either.
Let's say it's 254. So on this side, left side. So you see there the tank. Of course, you're not going to see these two over there. You're going to see one peak. But there probably is two, the pyrene and an impurity. In a regular UV detector, you won't be able to know that there's two in there. But then when you run a PDA, you see two different spectra for each of these, the pyrene and the impurity, and then you will know, okay, this is not a pure peak. And I hope Nigel showed you a peak that wasn't pure on PDA in the lab. So PDA can detect, but sometimes it has limitations. Some compounds, they might be molecularly different, but they have the same functional group that absorb light, but they're different. We talked in the MS lab today about isoflavones, and then they share this one aglycone that is the one that absorbs light. So they will have potentially the same fingerprints, but they might, because one has sugar and one doesn't, they will elute differently based on their polarity. But they will have the same wavelength because they have the same group that absorb light. So it has positive and it does have a limit of its capabilities. But what I want you to know, PDA gives you kind of a better information about your compound than just absorption at one wavelength. Okay. We'll talk more about PDA and variable wavelength detector under spectroscopy. Now, fluorescence is another detector that can be linked to HPLC. And here, instead of measuring absorption, you measure the fluorescent light. So some compounds are capable of not only absorbing light, but emitting light in a measurable manner. Amount emitted can be measured and gives you much better sensitivity. So we can measure fluorescence. We'll talk about fluorescence in more detail under spectroscopy. So far, UV detection or fluorescence detection. Refractive index, I'm sure you're familiar with the refractive index. And it is very specific to the concentration and the composition of the sample. So you start with measuring the refractive index of your constant mobile phase. And then when samples start coming out, there is a change in the refractive index. That change in the refractive index is correlated to concentration. So you would do standards and you will correlate change in refractive index to the concentration. Now, in this type of spectroscopy, not spectroscopy, sorry, detection, you cannot use gradient illusion. Because when you use the gradient illusion, you're changing the composition of the mobile phase. That's going to affect your refractive index, and it will interfere with your detection of your compounds effectors. So refractive index is usually run with the isocratic mobile phase, and very common for sugars and carbohydrate and lipids when they are abundant in high concentrations. Another one is electrochemical detection. There is the PAD, not PDA, pulse amperometric detector, which is based on oxidizing or reduction of a compound using a voltage, and then you measure the change in current. That's one form. Another form is measuring a change in conductivity. And then there are examples of where it can be used. Light scattering is a universal detector. Make sure you note that. It's a universal detector. It detects anything and everything. The compound doesn't have to be a chromophore, for instance. So the way it works is you have your compound being carried by the mobile phase. And it reaches this detector, the mobile phase is evaporated by heat. And then the compounds hit the light source. And then the scattering of the light is related to the concentration and the characteristic of that molecule. It's commonly used with size exclusion chromatography, SEC, size exclusion chromatography. And the MALS is multi-angle light scattering. So this is highly sensitive and is used if we want to get accurate molecular weight of the compound. Of course, MS is a detection, so it's a detector. And chemical reactions. So if we're looking at amino acid composition, for example, do all amino acids have chromophores in them? Can you name the 3 amino acids that have a chromophore or can absorb light? Those that are taking fit chemistry, have you gotten to the protein lecture yet? Tryptophan, huh? Aromatic, yeah. So tryptophan is one. Tyrosine, and one more. Phenylalanine. These are the only 3 amino acids that absorb light, but all proteins have them. So if we are measuring protein or detecting protein, we can do UV detection. But if I'm detecting amino acid composition, I broke down my protein into individual amino acids, I won't be able to detect all of them using UV. So I derivatize to make them have color or to fluoresce. So I use OPA, which is a fluorescent, and I use or anhydride, which give you a color that you can measure absorption. Okay. Questions? All right, this is a good table. When I ask you, give me an example of an analyte using different separation modes. So this is a good summary table 13.1 in your book. And then we already talked about normal phase, hydrophilic interaction chromatography, which is a chromatography similar to normal phase, but uses different mobile phases. So you can use, for example, acetonitrile as a solvent in hydrophilic interaction chromatography. What we call it, helic. So, and then you can add a mass spec interface to it, and it's commonly used when we do peptide mapping, meaning when we digest a protein, we map the peptides generated by different enzymes used to digest the protein. So we use helic to identify those peptides. Lipid metabolites. So when lipid break down into different metabolites, we can use helic to identify them, organic acid, or even monoglycerol, acylglycerol, diacylglycerol. And then reverse phase, we have the example caffeine, alkaloid, and a whole slew of different compounds, pesticides, mycotoxins, antibiotic, and so on. Ion pair reverse phase. So in this situation, if you have compounds with a charge, you can suppress the charge on that compound. Then they can interact with a nonpolar stationary phase, and you can separate them using reverse phase chromatography. Here are just chromatograms and examples of separating different bran oil that you have tocopherols in that, tocopherols and tocotrienols. And then here is an example for vitamin B6 compounds. In ion exchange, anything that you can make it have a charge. So amino acid, they have a charge. Proteins, they have a charge. Carbohydrates, do they have a charge? No, they don't. We make them carry charge. They are very weak acids. So at high pH, they can deprotonate and become negatively charged. We'll talk about that under the carbohydrate lecture. Yeah, so anything with a charge can potentially be a candidate for ion exchange. Size exclusion, it's not as commonly used, but we use it a lot, for example, in our lab when we want to look at molecular weight distribution of proteins. We use high performance liquid chromatography in size exclusion. But a lot of the application is for separation and fractionation and collecting fractions under low pressure. Affinity, it's very specific chromatography, specific interactions, mostly used for glycoproteins, allergens, enzymes, mycotoxins, antibodies, things like that. These are just examples. And now, in the last 10 minutes, I want to do this exercise with you. All right. So, what you see here is a series, I think 11 or 12 isoflavone standards, which are, these isoflavones are phytochemicals that we monitor in different crops. One of them is soy. It has a lot of them. They have good physiological benefits. So there are a lot of studies on them. Anyway, this is the gradient that we use to get those standards eluting like that within 60 minutes. So we start at time 0. So this is the gradient, how we build it. We start from 17% acetonitrile. We go up to 25%, 25 minutes. And then from 25 minutes to 30 minutes, we keep it isocratic. Then we increase to 30% between 30 minutes to 40. Then we keep it isocratic for 10 minutes. And then we bring it down back to 17. We leave it about 8 minutes to kind of, we call it equilibrate the system before we inject again. We need to bring back the system to the original state. All right, so here are your questions. Is this normal phase or reverse phase chromatography? Huh? How did you find out, Sophie? Yes, it is correct. But if you didn't look at the picture and you're just looking at the gradients, acetonitrile is an organic solvent. So say that again. The other 83 is going to be water. So we start with polar, and then we take it, we increase the acetonitrile, so it's becoming less polar over time. So when you start with a relatively polar mobile phase, then your stationary phase is relatively non-polar, and that's reverse phase. Okay, so from this you can tell that, okay, I'm increasing the acetonitrile, so I'm increasing the organic phase, then the polarity is going down. That means it is reverse phase. Okay, good. Which isoflavone is the most polar? The one that elutes first or the one that elutes last? Elute first. The most polar would want to interact the least with your column and will come out when your mobile phase is polar, mostly polar. Very good. So the most polar is the first one, just before 10 minutes. Okay. How would you change the mobile phase? So genistein, I didn't label them. So the last one over here is genistein. Okay. I thought I had this labeled. I don't know what happened. Okay. So that genistein would elute sooner without changing the relative positions of the other compound. So we have between, let's say, 33, 35 minutes and 50, we have nothing. And genistein is coming out at around 49. How would I change this, the gradient, so that genistein comes out sooner without impacting all of these? Wait, Sophie. So no, but you can tell me, forget about pH. Tell me about yourself about what do you increase the temperature of what nothing cool, but do you want to increase it from the beginning? Because you don't want to impact those first ones. If there is a way to increase the temperature after 35 minutes, yes, you can do that. I didn't think of that answer, but it's still a valid answer. Thank you. And other way of doing that.
You keep increasing the acetonitrile concentration after 35 minutes.
Yes. So we did plateau here between 40 and 50 minutes. We did isocratic, but we don't need to. We can keep going up, let's say, to 40% acetonitrile before we drop. So this might come sooner. Okay, these are options. If you're able to increase the temperature and not damage the column, do that after 40 minutes, but mostly is increasing acetonitrile a little bit more past the 40 minutes. Very good. What would happen if you keep an isocratic elution mode at 17% acetonitrile? If you keep it at 17, Isocratic from beginning to end. What do you think is gonna happen? Well, longer elution time and broadening of the peaks as well. So taking more time on the column than they need to. And some of the peaks will broaden, especially those in the middle. And we might lose separation. Okay. And longer elution time. We don't want that. We don't want more time for analysis for sure. What would happen if you keep an isocratic elution mode at 30%? So you started at 30% and kept it. So you started at 30% acetonitrile and kept it.
Would you need a bunch of correlation?
Or bunch of coelution. Everybody would want to leave the column. They don't want to separate. So it's very high organic solvent concentration that the compounds don't want to stay on the column anymore. And without staying on the column, you don't get separation. So you don't want that. Okay, very good. So you can do liquid chromatography in tandem, like different modes of separation, 2D and 3D. And this is often done when you really want to purify and identify. This is very common in protein analysis because proteins are, or in this case, peptides, they have similar characteristics, but you really want to know which peptide, for example, in this example, is the most potent or have the highest antioxidant, so you can produce more of it and use it as a pharmaceutical product. So what you do is, if you're hydrolyzing your protein to produce bioactive peptides, then you have a mixture of low molecular weight peptides, a little bit medium, a little bit large, but you know that your most potent will be the smaller peptide. So the first thing you do is you filter. So you ultrafilter, you get the permeate, so the ones that pass through the membrane of small pores, and you throw out the retentate, what stays on the membrane. So you take those the permeates that passes by, or filtrate or permeate, they mean the same thing. And then you run them through ion exchange, followed by size exclusion, or size exclusion followed by ion exchange. Doesn't matter the order. But what you get, if you do, let's say, size exclusion first, doesn't matter. You get different fractions. These fractions are not pure because you might have peptides of the same molecular weight, but they have different characteristics. But you did get some fractionation. You take each fraction and you do an assay for each fraction, antioxidant assay. And you determine the fraction G or F that has the highest bioactivity or antioxidant activity. You take that fraction and you run it on ion exchange. Now you are separating based on charge. So those peptides that have the same size are now separating based on charge. You get the fractions, you measure the antioxidant, you take that one fraction with the highest activity and you run it on reverse phase chromatography. So because now the peptides that may be of the same size, of the same charge, might have different polarity. So you separate them again, and at the end of the day, you want to get this very pure, most potent peptide and sequence it. So you can run it through C-terminal or N-terminal sequencing, or run it through MS to get its sequence. And then you can produce more of that one fraction. Long story short, use HPLC in tandem. You can purify as much as you can and then identify. Okay. Reached the end. I didn't have time to start spectroscopy. We'll start spectroscopy on Friday.
Sent me the background.
Okay.
No, I just.